She's now a professor at Rutgers. She did her graduate studies with Mark Braverman and then postdoc at Stanford with Omer Reingold. And today she will talk about, Sumegha, can you share your slides?
Yeah.
Just to make sure that it's like, okay, on online omniprediction. All right, so Sumegha, you can take it away.
Okay, yeah. Thanks, Rafael, for the introduction. And I would have loved to be in person, but
now we cannot hear you.
Yesterday. You can't,
Unless it's just me, or
it's just you. We can hear her.
I hear you. Yeah, I hear you well.
I cannot hear Saper either. Okay, great. So it's just me. Okay, keep going. Then I will organize. I will figure out how to listen to you. In the meantime, I'll read your lips.
Okay. Yeah. Thanks for the introduction. Sorry, I'm in Waterloo, but I couldn't be there in person because I got cold or like fever yesterday. So today I'll be talking about this work with Chris, Omer, and Aaron on online omniprediction. The outline for so please feel free to interrupt me with questions and clarification questions or any comments if you have in the middle. Okay, so let's start. So the outline for this talk would be, first we'll talk about like regret minimization, which will motivate the notion of online omniprediction. And then we will see its connections with fairness notion, which is multicalibration. And especially like these connections had been established in the batch setting between batch setting omniprediction and batch setting multicalibration. And we introduced the notion of online omniprediction. And then we'll study some new algorithms that we achieve for multicalibration and hence omniprediction. And then I'll end with some open questions. Okay, so let's start with what is a prediction task. So a prediction task is you are given you have individuals and outcomes. So for example, let's say the individuals are represented by a feature vector X and the outcomes are represented by Y, which is a label. For this talk, we will consider it to be a binary label. And then so we can think of these labels as like, for example, whether this individual will repay the loan or not. And then so we were given training data, which is a set of individual outcome examples. And the goal of the prediction task is to output a predictor that, given a feature vectors, predicts the outcome on that feature vector. When we talk about the batch setting, we assume that this predictor needs to predict on a given distribution. So that means that you are given a distribution on feature and on individual outcome examples, and you want to have a good predictor on the training data is achieved is drawn from this distribution, and your guarantee is also that the predictor needs to be good on this distribution. So the optimal algorithm or optimal predictor would be the Bayes optimal predictor, which looks at every feature vector and under this distribution sees what is the probability of Y equal to 1 given this feature vector, and then outputs that. But the Bayes optimal predictor, there are multiple problems with the Bayes optimal predictor. One, it is sample heavy. That is, it needs a lot of samples to figure out, like, you need to at least see each feature in your data set to predict to output this P star X. And then the second problem is that even if we get all these samples, this might be computationally heavy to express. So the one way to express is using a data structure for like using an array for every X, but that might be too computationally extensive. So that's why we, in the ML community, we move to loss minimization, where we want to, under the loss minimization, we are given a class of hypothesis, which is capital F, and then we want to figure out which function amongst this capital F does the best on this distribution in predicting the labels given the feature vectors. Now, when you're talking about these, what do we mean by best? The best means that now we pick a loss function and then we measure that according to that loss function, which f is minimizing this loss function. So the very common losses that are used is the L2 loss. This is the exponential loss. This is the L1 loss. So and the point is that for different losses, you might get a different function f that is minimizing that loss. And so this is the batch setting. Let's talk about the online learning setting or the online setting. So in the online setting, at we still receive feature vector common label pairs, but there is no distribution. It's a distribution free setting. So at the tth time step, feature vector common label pair arrives, xt comma yt. The learner or the algorithm that wants to predict sees xt, but and takes some action at without seeing yt. So you don't see the label, and so you're taking an action before seeing the label. And the loss incurred by the learner at the tth time step is given by some loss function L, and the label that is the label that was seen at the tth time step and the action that it and the action that it took. So what is the goal? A high level goal is you want to take optimal actions with respect to the benchmark class capital F. So this is similar to how loss minimization, but just in the online setting. So formally, the goal is to minimize regret. That is, if in the end, after I have performed all actions, if I shouldn't have regret, that is, oh, I should have just I took actions according to this particular function f in my class capital F instead of taking my actions. So we want to minimize this regret. No, this cannot be 0 because this is a distribution free setting. So in the starting, I don't know anything about how YTs are being generated. So it's impossible to get 0 regret. Okay, so some known facts about regret rates. So this is the problem of regret minimization, and many people might already know this. So even for constant f's, so that means that even if you have only like the all zeros function and the all ones function, then also if your loss is L1, then you need at least 1 by square root t regret. So as t goes to infinity, your regret is going to 0, but for a fixed number of time steps, you incur at least 1 by square root t regret. And then there is basically the like there are certain complications, but these regret rates are like the whole community has been about like these regret rates are achievable. So for example, there is an algorithm that achieves regret of log to the size of the concept class divided by t. Any questions?
Yeah, sorry. So let's say you're saying that like regret 0 is impossible, but what are the assumptions? Because somehow if I have like let's say that I picked one function f from my set capital F, and that was the function minimized, right? Wouldn't I have regret 0 for that particular instance?
So yeah, so I guess f contains at least 2 functions, let's say capital F.
Right, but even if I pick the right function that minimized for the inputs that I see, right? Wouldn't I have regret 0?
You would, but then you wouldn't know. So these YTs are generated in any way. So you want to say that for all sequences, what is the maximum regret? So for all YT sequences. So there would be a YT sequence where this algorithm won't work.
So there's a worst case here that.
Yeah.
Okay.
Okay. So what if there are multiple learners with different losses? So one way is like, what do we mean? But like everyone wants to minimize their regret, but there are different losses. So one of the motivations for this is, what if if all of us use these forecaster for like the forecaster or like weather predictions to detect if there would be rain today or not. So there is a forecaster that is predicting whether it would rain today or not, or in general, like let's say we are trying to predict whether it would rain today or not, and there are different people who are using the same task to do different actions. So for example, I might say that with whether it would rain or not, depending on that, a farmer would plant their crops or not, or a fisherwoman might go outside to fish or not. So similarly, like whether I will go to office or not. So the threshold at which it would rain or not depends on it makes based on that, like what is the actual probability of rain. I will make my decisions based on that. So this means that all these agents are optimizing for a different loss, or like are trying to minimize regret with respect to a different loss. But we don't want to run an online regret algorithm per agent. So this motivates the notion of online omniprediction, which is we want to output a single forecaster that can be used for regret minimization for multiple losses simultaneously. So let's see what is the setting. The setting is like the forecaster. So for example, like Apple weather map, a forecaster says it's going to rain with probability PT. Now I just look at this probability and then based on this prediction PT, I take an action AT. So I do it doesn't matter what was XT, but I'm just taking actions based on the probability based on the prediction probability PT. So the formal setting is at the tth time step, XT YT arrives, and the forecaster sees XT. After making a prediction PT, it sees YT, that is the label. And a learner, so there are three players now. There is a nature or the adversary, there is a forecaster and a learner. Forecaster is seeing XT and making prediction PT, whereas a learner with loss L uses a simple post-processing function to choose its action at the tth time step. So based on PT, it applies some simple post-processing function to take the action AT. So what is this simple post-processing function? So it's what we would intuitively want. If the true probability of rain is as predicted, what would be my optimal action? So this is, let's say my label is actually drawn from the predicted probability. And then what is the action that what I would take to minimize this loss? So for one of some examples of this is like if it's an L1 loss, then I would basically do rounding. If it is above 0.5, I will output 1. If it's less than 0.5, I'll output 0. If it's an L2 loss, I'll output the PT value. Any questions on the definitions of optimal action? Okay. So then, okay, so what is the regret for a learner? So a learner has a loss L. It uses a simple post-processing function to choose its action. And then the regret is basically you are still comparing to a concept class capital F that has been given to this online omniprediction setting. So you see what is my average loss if I follow this predictor PT minus the regret minus the minimizer for the loss from this, if I choose the F from this concept class capital F. So this is the regret for this one learner which had loss L. Now, what do we want? We want that for all L in this class capital L, this regret should be small. Let's say sublinear in T. Ideally, we would want alpha to be half. But for now, we are saying that it is it's sublinear in T. So this is so we want to, so this is the notion. Omniprediction is PT, like my predictor is an omnipredictor if it has this guarantee that no matter what loss I give it, no matter what loss I'm using from this concept, from this large class capital L, my regret is small. So the point is that it might seem to be a strong guarantee, but it can be achieved, and it can be achieved efficiently. That means that given an oracle for online learning, we can achieve it. Okay, any questions on the definition? So how we achieve online omniprediction? Before we look into that, let's look at what were the results in batch setting. In the batch setting, omniprediction was already defined in 2022, and there are many recent works on omniprediction, and they show that how to achieve omniprediction. Either you can achieve it through multicalibration, or you can achieve to calibration plus multi-accuracy, and so on. So there are already a lot of works in the batch setting, but there weren't any works in the online setting for the omniprediction. So we will look at like one of these ways, that is like how to achieve omniprediction using multicalibration. Before we go into that, let's see. Let's look at what was the definition in the batch setting for omnipredictor, and what is the definition of multicalibration. So in the batch setting, you are given a distribution. On individual comma label pairs, feature vector comma label pairs, and then F is the class of hypothesis, and then you want to minimize the loss, expected loss that an F from the concept class capital F incurs if we make the predictions according to capital small f. And then omniprediction is you want to output a single predictor such that for all losses, you have that if you do actions or if you predict according to this predictor, then your loss would be less than any loss that can that a function in this concept class capital F can incur. So let's do some sanity checks. So another notion could have been, instead of having this post-processing function, we just have that this is one predictor that minimizes loss for multiple losses. So but the point is that is not achievable, because depending on the loss, if it's an L1 loss, then you don't want to L1 loss versus L2 loss. L2 loss is minimized when you do a non-binary outcome, whereas when you do use a non-binary prediction, whereas L1 loss is optimized when you do a binary prediction. So even like if you knew the base optimal predictor, the base optimal predictor would not satisfy this notion. So then that's why you want that, given the loss, you want to do some post-processing function, on the predictor to output the to get this omniprediction guarantee. Okay. So exactly as I said, when you have this definition, your base optimal predictor is an omnipredictor. Let's see that. So if you have a base optimal predictor here, then you know that for every feature, not even just on the distribution, for every feature, you are taking the optimal action or optimal prediction. You are doing the optimal prediction with respect to that feature vector. So even if you do averages, it would always be, the left-hand side would always be less than equal to the right-hand side. So the base optimal predictor is definitely an omnipredictor. And then the question is like, do you really need to find the base optimal predictor, or can you get away with some efficient predictor, which is also an omnipredictor? So what do we mean by efficient? So for a single loss, if you have a single loss, this is the setting of agnostic learning for class capital F. And we want to say that if you can do agnostic learning for a class capital F, then you should be able to find this predictor too. So this is the Oracle efficient. So if you can't do agnostic learning for this class, then even for multiple losses, how can you optimize? Even if you can't optimize for a single loss. So this loss, so the loss class that we consider here, or like this paper considered, is the class of Lipschitz convex losses. So we say that a loss is convex in the action space T if for all if it is convex in the action space T for both the labels 0 and 1. So that means that L0, T is convex and L1, T is also convex. And now this is the connection that if your predictor P is actually multi-calibrated with respect to this class capital F, then it's also an omnipredictor with respect to the loss class of all Lipschitz convex losses and the concept class of the same concept class as F. So this is saying that if a predictor, now you're going away from like the omnipredictor guarantee, you're just saying that the predictor needs to be multi-calibrated, then it already gives me the omnipredictor guarantee. Any questions? Okay, so this multi-calibration was introduced in this paper of Herbert, Kim, Reingold, and all. And it said that multi-calibration is achievable using weak agnostic learner for capital F. So if you have an agnostic learner for capital F, then you can also achieve multi-calibration with respect to capital F. And then this implies that you can also achieve omniprediction with respect to benchmark class capital F, if you have a weak agnostic learner for capital F. So let's look at like what do we mean by multi-calibration. A predictor P, which takes in which outputs a value between 0 and 1 and takes in a feature vector X, is calibrated if for all values V in 0, 1, you have that when I condition on X on P of X equal to V, then in expectation my actually the number of people whose outcomes are 1 should exactly be equal to V. So this means that the predicted values mean something. So if I look at all the individuals who I have given the score of V, that is like I'm saying that, okay, all of these individuals, I'm saying that like you are going to repay the loan with probability V. That is what I think. So it is my predictions are calibrated if amongst all these individuals, actually V% of the people or V fraction of the people repay the loan. So this is the notion of calibration. I won't go into the details. Approx calibration is basically like, now instead of like, because there are like infinite values in 0, 1, this is usually unachievable. But how you achieve it is by making it buckets. Like you do not output you discretize this 0, 1 space and then make your predictions. And then you say that like all the if I condition on all the individuals, I'm giving approximately V value, then the number probably then the fraction of people that will repay the loan is also approximately V. So this is the notion of approximate calibration. So calibration is when you talk about fairness, calibration is actually a nice notion. we can show that even like many of the real world machine learning algorithms are not even calibrated on certain subgroups. So this is why it's also a fairness notion that you want that your prediction should be calibrated. But it's not an enough notion, that it's not enough, like, because one way to achieve calibration is you predict mean for everyone. And this is not a useful predictor. You predict, you are bunching everyone in this one bucket of the mean, and then saying that, okay, this is calibrated. So, and then the another thing is that, as I was saying, for different subpopulations, you might be overestimating and underestimating the real probability. So you might be calibrated, but if you really look at like a subpopulation, for those subpopulation, you might be overestimating the probability of repaying the loan, and for some subpopulation, you might be underestimating. So that's why this is a fairness notion, that you want that you are calibrated even on a subgroup. So let's say S is a group that you really care about. Then you want that you are calibrated, that is your expected Y condition on your predictor giving this V value, and that X belongs to this subgroup S is also V. So that if you just look at individuals in this subgroup, then also your predictor is calibrated. So the next question, so that's why this is a fairness notion. So you can be like, okay, you have like two groups you care about, so you want that you are calibrated on both the groups. But the more important question here is like which groups to protect. Either they can be like historically disadvantaged groups. This paper in 2018 took this approach that you actually want calibration with respect to all computationally identifiable groups. So if you can identify a group computationally, then you want calibration with respect to that group.
So I got a quick question.
Yeah.
Like conceptually, I think I'm trying to understand calibration. So if you have an ideal predictor, then you will get calibration for every group that you want?
If I have the Bayes optimal predictor?
I guess so, yes.
Yeah, so Bayes optimal predictor gets calibration because, in fact, Bayes optimal prediction is expectation Y conditioned on P star X. So expectation Y conditioned on P star X is some value. It's exactly equal to P star.
Yes, yes.
So that's why Bayes optimal predictor would be calibrated.
Got it. So calibration it's not really a trade-off between accuracy and calibration. They're actually going in the same direction, yes?
Yeah, we are going in the same direction.
And you're saying still there are good algorithms that are good predictors, but they're not calibrated?
Yeah, so one of the things is like depending on the loss. So for example, if it's L1 loss, then you will not get it calibration. But if it's L2 loss, if you're optimizing with respect to L2 loss, then you will get calibration. But the point is that if the loss is optimized to 0, but if there is an error, then again you lose calibration.
Got it. All right.
And then the second thing is like we don't have, if you're doing distribution, the loss minimization on the entire distribution, there would be some subpopulations where you won't be calibrated. So it can be thought of as like multi-objective minimization for different subgroups.
All right, thank you.
Yeah. So this paper is like computationally identifiable groups. So what do we mean by computationally identifiable groups? So this means that the membership function, that is like whether this the feature vector belongs to this subgroup, is a computationally efficient algorithm. So this is on high level what it means, but for more formally, one of the examples that they give is that let's say you have like decision trees, like small depth decision trees over these feature vectors, and that is identifying whether a feature vector belongs to this subgroup or not. So what is multicalibration? So multicalibration is a predictor P is multicalibrated with respect to a class of Boolean functions given by in Boolean functions in capital F, if for all functions in this capital F and for all values in 0, 1, you have that the expected Y conditioned on f of x equal to 1 and p of x equal to v is exactly equal to v. That is, if you look at only the feature vectors on which this f value is giving me 1, then my my predictor my predictor is and a condition on the predicted value, then my expectation of y conditioned on these values is exactly equal to v. So, okay, so even if you are not completely intuitively understanding this definition, another way to write this is that if I condition on a px, I condition on a score group of my predictor, that is all individual feature vectors on which I'm giving approximately v value, then my f of x is uncorrelated with y minus p of x. So this is another way to write this. And when we write this, when we rewrite this as an expected correlation thing, then it is also generalizable to non-Boolean functions. So this is something that is going to be useful, that your function value is uncorrelated with y minus p of x if you look at p of x. That is, like, knowing f of x is not giving you any advantage beyond p of x. So you might start understanding why it is also a useful notion in omniprediction, because if f is not giving me any advantage because there is no correlation with y, then it cannot give me advantage even in loss minimization. And to make it formal, and you can make it formal to get an omnipredictor that is, if a predictor P is multicalibrated with respect to class F, then it is an omnipredictor with respect to the benchmark class capital F and the loss class, which is the set of all Lipschitz convex losses. Any questions? So, so the reduction proof, the proof is, so I wanted to do it on the board, but I guess now it's not possible. But the on high level, the proof is that you look at a prediction value V and a particular loss L and the particular hypothesis capital F, and then show that your predictor actions according to your or according to the prediction are optimal, and F cannot give you any better loss. Exactly. So basically you prove that because the action is defined as this, KL of V is argmin of T, such that if Y was being generated from Bernoulli V, then T is the thing that optimizes it. And now when we look at this, because it's multi-calibrated, you can assume that Y is actually being generated from Bernoulli V. And then instead of F, and then there is some work that goes into proving that because F is uncorrelated with Y minus V, that means that this accounts to actually taking the same action, which is F of X, regardless of what is my value value on Y. So this means that we are now comparing this optimal action against the action that is being taken by F, which is only one action. So that means that our action would be optimal. So yeah, so it might have I think I wanted to do it on board, but but I hope that at least like intuitively it is clear that like why this multi-calibration notion can help. Okay. So let's come back to the online setting. So in the online setting, then we might be like, okay, if we can get online multi-calibration, then we can get online omniprediction too because of this connection.
Hi, Sumegha, can you hear me?
Yeah.
Oh, sorry. Can you go back to the reduction proof? So yeah, what is the intuition here that this action incurred a loss less than that incurred by F?
Yeah, so if I look at a particular prediction value V, then f of x might be like different, like all the features that are that all the features that my predictor is giving value V, f of x values are very different. But one step we argue that basically the loss incurred by f is similar to, because it is uncorrelated, it's similar to so I guess because it's a convex function, you can be like if on y equal to 1 value you give the mean, then my loss will only decrease, and if on y equal to 0 also I give the mean of f of x.
Okay.
And now the point is that now we use multi-calibration to say that these mean values are same, because this mean values needs to be same, a condition on this prediction value y, because there is no correlation with y.
Okay, I see. Okay.
So now you are comparing your optimal action with just one action, which is the mean of f on the entire prediction value v.
Okay.
So now your optimal action would be optimal because this is how it is defined.
Okay.
So yeah, so the argument is like you want to say that the variations in f don't help. You're basically because there is no correlation.
Okay, thank you.
So coming back to the online setting, we extend this connection between multi-calibration and omniprediction to the online setting. This is kind of straightforward. The proof, because the proof is like does not use the any batch. You're just conditioning on all the features that achieve this value v. The proof goes to the online setting. But one of the things is that for online multiple calibration, we did not have reduction to agnostic learning as we had in the batch setting. So this is the new part in the paper, that where we show a new Oracle efficient online multi-calibration algorithm. And then the third is that we also give an algorithm that doesn't go through multi-calibration. This is like, so this question has been answered by other papers also simultaneously, but we also answered this, that multi-calibration is not necessary for getting omniprediction. Or even like calibration is not necessary for getting omniprediction. So what is some related work on multi-calibration? Now we have moved on to like just getting optimal algorithms for multi-calibration. So calibrated forecast was defined in this paper by David in 1985. It showed that if my predictions are actually the correct predictions, then I'm calibrated. So this goes back to the question of that Saper asked in the batch setting, because of how it is defined. Calibration is it is like trivial to see that like omnipredictor or sorry, not omnipredictor, the Bayes optimal predictor is calibrated. But in the online setting, because there is no distribution and there is no it's a distribution free setting. It's not clear that even if we can achieve calibration at all. So if my predictions are actually generating the labels, then we can do some like law of large numbers to show that the if I look at the sequence, if I look at the sequence of x comma y pair, xt comma yt, then it would and comma pt, then it would be calibrated. So the next question is that, like, even now, if we don't know, like now this goes back to this question that, like, we want a guarantee that is that for all sequences, you want calibration. You want an algorithm that is calibrated for all sequences. So this is this paper, papers by Foster-Vora in 1998, and these papers showed that there at least exist forecasters that are calibrated, and this existence is it's not non-constructive. It goes through a minimax argument. That is, like, if you knew nature, then you would you can output calibrated predictions, and then now using a minimax argument, you can show that there exists a forecaster, randomized forecaster, that can achieve calibration in expectation. So this is important. Like, there exists no deterministic algorithm that can be made that can be that is calibrated with respect to all sequences. So why I'm saying that it's important for all sequences, this is like, no matter what is how the nature is playing the game, we want calibration. And this is something that is achievable. Like, for example, like you outputting just the mean, but there is no way to output the mean in the online setting. Because it's coming one day at a time. So then there are these papers that also give explicit constructions. These go through like having a min-max, doing a min-max argument every day. And we are going to talk a bit more about this paper by Gupta et al., which actually showed an explicit construction for multi-calibration. And then there are like various works in online learning. So in some sense, we are trying to minimize multiple regrets at the same time. But there have been various other notions of regret in the online adversarial setting that optimizes for several objectives simultaneously. For example, sleeping experts, adaptive regret, swap regret, etc. But all of these seek to minimize the same loss function on different subsequences of time steps. Whereas we are looking at the entire sequence of time steps and trying to minimize different loss functions. Okay, so what is going to be important so one of the things that I mentioned in the starting was that we want to get a sublinear regret for online omniprediction. That is, we want to output a forecast or a predictor such that we want to have a forecaster or a prediction algorithm such that for a lot of losses, it gives a sublinear regret. But ideally, we know that if there is a single loss for many of these problems with respect to benchmark, for many of these benchmark classes, we can get like 1 by square root t regret. So we might want that to be the optimal, that we want like 1 by square root t regret, even for online omni prediction. Now this error, the error in loss or the regret in online omniprediction comes from what is the error in multi-calibration. And now it becomes important for us to, till now we have been like, okay, let's assume that the error is 0. Why does the reduction work? But now we need to talk about like what is the error or like how it is represented. So the error for f and a prediction value v is you look at all the time steps where you predicted v, and then you look at the correlation of f of x and yt minus v. So this, if it is perfect multi-calibration, this would be 0. But what is L infinity multicalibration? L infinity multicalibration is you max over all the prediction values, this error multiplied by the number of the fraction of time steps you actually outputted, you predicted V. Now, if this is so that's why, like, if we don't have this, then again it becomes hard to achieve this, because you want error to be small even on rounds where you did not predict. So that's why you have this notion, you multiply it with the probability of, or like the fraction of time steps where you actually predicted this value V. What is L1 multicalibration? L1 multicalibration is basically you sum over V. It's not max over V. You sum over this V. So this is expectation over V, that is exactly sum over V, probability that the number of time steps that you actually outputted V, and the absolute value of the errors. And then L2 multicalibration is you do the square. What this paper by Gupta et al. Showed that you can achieve online multicalibration with error rate of square root of log f by t, but they showed that you can achieve L infinity multicalibration with respect to this, with this error rate. So this is the error rate that we want, but L infinity multicalibration is not enough to do omniprediction. You actually want an L1 multicalibration. So L1 multicalibration, because there is a way to go from L infinity multicalibration to L1 multicalibration, but you have a loss in the regret rate. So here you get that it's your regret is less than equal to square root of log f by t to the 1/4. The previous paper showed that L1 multicalibration is enough for omniprediction, and this proof goes through even in the online setting. So this tells you that we have achieved online omniprediction for Lipschitz convex losses with a regret rate of log f divided by t to the 1/4. So the alpha or the sublinearity is 1/4 instead of 1/2. Now the question is, there are two questions. What about real valued hypothesis classes? Because here, if the real valued hypothesis classes means that the size of f is infinite. So usually when the size of f is infinite, that's why in ML we define like these combinatorial dimensions, so that our regret rates are in terms of these combinatorial dimensions such as Rademacher complexity or so on. So this is so we want to replace this log f with some complexity. Second is, can we get better regret rates? Which is like instead of t to the 1/4, for even like for finite hypothesis classes, can we get better rates? So we answer both of these questions partially. Before that, for the second question, I want to notice that if we want to actually get better rates, we need to have an algorithm that does not go through multicalibration. Because this paper by Mingda and Greg in 2021 showed that you can, for L1, you cannot get L1 calibration with error rate better than 1/t to the 0.48. That is, like, you cannot get L1 calibration with error rate of 1/√t in the online setting. So we need to develop algorithms that does not use L1 calibration to prove omniprediction. Okay. Sorry, how much time do I have?
Can you hear me?
Yeah.
Yeah, I think 8 minutes should be good.
8 minutes. Okay, sounds good. Okay. So what about real valued hypothesis classes? So instead of going through L infinity multicalibration, we go through L2 multicalibration to get some instead of log f to get Rademacher complexity there. So L2 multicalibration, the nice thing about L2 multicalibration is like the loss becomes the squared loss, and somehow it's nice to deal with for Oracle efficient algorithms. So if you can get an L2 multicalibration with the rate of t to the minus alpha, you can get an L1 multicalibration that with rate t to the minus alpha by 2, and which gives you omniprediction. So through this route, also we do not get optimal regret rates, but at least we can we have an online multicalibration algorithm for infinite hypothesis class. So yeah, so I guess like if people are interested in talking about it, I can talk about it some other time, but like I won't go into the details of the Oracle efficient algorithm, but just say this, that in the batch setting, these papers had showed that there is an equivalence between squared loss minimization for every level set and multi-calibration. That is, if you do squared loss minimization for every level set, a level set means that for every value v, then you get multi-calibration. So we use this connection for the online case, and then basically having some loss minimization for every value of v is similar to having a swap regret kind of guarantee that you want to reduce swap regret in the online case. So for using algorithms for swap regret, we can get algorithms for L2 multi-calibration, and this reduces online multi-calibration to solving online squared error regression over the class capital F, which know that, for example, for linear regression, this can be done efficiently. Okay, so can we get better regret rates? We actually show an algorithm that achieves like log f divided by square root t regret, but only for finite hypothesis for Boolean hypothesis classes. So that means that this algorithm does not go through L1 multi-calibration, but this algorithm uses this characterization. So this is by Kleinberg et al., which implies that it suffices to have omniprediction with respect to a finite class of losses referred to as V losses. So what is this paper saying? Why is it useful? This paper is saying that if you want omniprediction with respect to these bounded losses, you can for binary variables, so for binary outcomes, you can instead just look at these special losses, which are V losses. So there are finitely many of them if you do some grid. So there are finitely many of them, and you can only look at these finitely many losses to figure out and if you have if you minimize regret with respect to these losses, this implies that you have minimized regret with respect to all losses. So now we have a finite function class. We have the finite number of losses. For this, we can have another algorithm. We don't need to use L1 multi-calibration. We basically hedge our bets and basically do a multi-objective learning with respect to these V losses and this finite class capital F. So basically for Boolean F, we can get a 1 by square root t regret rate. And for infinite F, swap regret algorithm gets sublinear regret for omniprediction. So yeah, so these are the results for online omniprediction. There are many open questions here. One of the things that I want to mention is that there is a stronger notion of omniprediction, which is called swap omniprediction. For that notion, we show that basically you cannot get a 1 by square root t regret because L1 calibration is necessary for this stronger notion. So this means that in our algorithm, which is the swap regret kind of algorithm, we also got this stronger notion of swap omniprediction. So if we want to get an optimal rate, we need to have only an omniprediction and not a swap omniprediction. Okay, some of the open questions is that can we get an Oracle efficient forecaster or even a constructive forecaster with L1 multi-calibration error rate of this? So We know that there exists a forecaster but that existence goes through a through a minimax argument. So, but we want an Oracle efficient forecaster that gets L1 multi-calibration error rate of 1 by t to the 2 by 3. Some people think that like this is optimal. You cannot get L1 calibration with better than this rate, but we don't know how to prove it. And then the second question is like for real valued high function classes, can we get tired rates or like even better than 1 by t to the 2 by 3? Okay, yeah, that's it. Thank you.
Okay, thanks, Sumegha. Okay.
Thanks.
Does anybody have more questions to Sumegha? Okay, so if not, we can thank Sumegha again, and then we can take other things offline. So thank you, Sumegha.
Okay, yeah, thank you.